Hello everyone, welcome to my channel. For those who are new here, by the way, I am Engineer J. I am a civil engineer and I am also currently teaching as an engineering professor. And in this video, we will talk about one of the most important topic in highway engineering, and we have here highway alignment. Now, in highway construction, we adopted important geometrical properties or geometrical concept. Okay, and these are simple curves, compound curves, reverse curve, and spiral curve. Okay, so what are the purpose of this curve? Now, one of the most common problems that we encounter in highway construction is the right-of-way problem. Okay, that's the most common cause of construction delay. Okay, and in order to avoid private properties na masagasaan or private properties that might be affected by our highway projects, we usually change the direction of our highways. Okay, and but however, in changing in direction, we need to consider that the transition is smooth as possible. Okay, dapat hindi abrupt yung change ng direction. For example, if you have a highway and then there is a private property here, so in that case, instead of creating a right angle direction, then you can create a smooth transition by adopting a curve. Okay, like that one. So by adopting curves in our highway design, this might prevent accidents. Okay, so we have different curves that we usually use, and then we have here the simple curve. Okay, then we have compound curve. Now, compound curve here, this is just basically combination of simple curves, two or more simple curves. Now, we have reversed curve is when we have combination of simple curves or a compound curves with opposite curvature. Okay, then we have also a spiral curve. Now, spiral curve naman, the difference is that in simple curve, we have constant curvature. But in spiral curve, we have a changing curvature all throughout. Okay, so these are the horizontal curves that we used in highway construction or in highway design. Now, where can we find a simple curve? Or we have here a picture. So this is an example of a simple curve. Okay, so basically, again, simple curve is used not to prevent, or especially when you want to avoid a private properties. Okay, if there is a terrains or an obstruction that might cause highway construction problems. Now, in our simple curve, we have several elements that we need to compute prior to the actual layout of our curve. So before we go to the field, before we lay out our simple curve in the field, we need to compute, or we need to determine the value of these elements here. Okay, so basically, when we want to plot our curve, so we positioned our instrument on PC. Okay, so we have our total station, or we have our transit positioned at PC. Now, PC here is what we call the point of curvature, or the point of the beginning of our curvature. Or in other words, this is the point in which our simple curve begins. Okay, now we also have PT here. Now, PT is the end of our simple curve, or this is what we call the point of tangency. Okay, now we also have the element here, tangent. Okay, this is the back tangent, and we also have this forward tangent here. And this back tangent here has a distance T. Okay, this one is T. Now, the point of intersection of these two tangent lines, forward and backward, is what we call the point of intersection, or that is what we call the PI. Now, what's the purpose why we need to compute the value of the T? Now, T again, that is the distance between PC and PI. The purpose of this is that when we want to change the position or the location of our instrument to PI, then we have this value T here. Okay, so that we would know the location of our PI, so that we will know where to transfer our instrument. Okay, that's the purpose why we need to compute the tangent. And the other purpose of this tangent lines here is so that we can lay out the exact curves of our simple curve, because this line here will be our reference line when we want to deflect. Okay, since we will be needing the deflection angle so that we can locate these points here along our curve. Okay, and this curve here is what we call the curve length. Okay, that's what we call the curve length, or that is the length of our simple curve. Now, the line that connects PC and PT is what we call the long chord. Okay? Now, we also have the external distance. External distance here, that is the length from PI to the midspan of our curve, or the mid-length of our curve. Okay? Then we have also the M. This one is the M, in which this is called as the middle ordinate, in which this is the distance from the mid-length of our curve to the mid-length of our long chord. If our long chord is C, therefore this one is C over 2, and this one is C over 2 as well. Now, simple curve is just basically a segment of our circle, or basically the arc of our circle. Now, if this is our circle and this is the center, let's say that's our center O. So, simple curve here is just this length here, okay? In which this is what we call the R, or that is the radius, and this is our R, the radius. And we have the this angle here, or the central angle, in which this is labeled as I, or the angle of intersection. Why is it called as angle of intersection when in fact it is on the center or inside of our circle? Since again, we know that this one is our tangent, okay? And the intersection, or the angle of intersection between these two tangent here is our angle of intersection I. Now take note, properties of a circle, the angle on this side here, or the central angle, is equal to the angle of intersection. Okay, this angle here is always equal. Okay, so this one, this is what we call the PC, and this one is our PT. Okay, now if we have this chord, okay, this one is our chord, the angle subtended by our tangent and our chord is the 1/2 of the central angle, or the 1/2 of angle of intersection, which is I over 2. Now, that is the properties of a circle. Okay, so please familiarize the properties of a circle. So these are the elements that we need to compute first prior to the layouting of our simple curve on the field. Okay, so we need to determine all the values of these elements. In computing for this element, we have this formula, the tangent distance. Again, tangent distance here are the distance of our back tangent and forward tangent. That is the length of these two tangents. Now take note, our simple curve here is always symmetrical with respect to this line. Okay, so therefore, the length of our tangent on the back tangent is equal to the length of our forward tangent. Okay, now tangent distance is given as R tangent I over 2. Again, I, that is the angle of intersection. Okay, then the middle ordinate, this one is the formula, R, where R is the radius, times 1 minus cosine I over 2. External distance, we have also the long chord and the length of curve. If you having a hard time memorizing or familiarizing this formula, so let's try to derive this formula by just using trigonometric concept. Okay, so let's derive all this formula. Now, the purpose or the advantage if you know how to derive this formula is that if in case you forget all this formula and you do not have a choice but to derive. Now, as what I have mentioned, simple curve is basically an arc of our circle. So this is our curve. Let's say this is our highway. Then we have this back tangent, and this one is our forward tangent. And then we have the radius from the point of curvature, or PC, to the center of our circle, and this is what we called our radius. correct? And from the center of our circle towards the point of tangency or the end of our simple curve, we still have here the radius as well. Okay? Then we have here the chord, okay, or the chord length, which is the line connecting PC and PT. Okay, again, this one is C, correct? And we have here this arc here, which is what we call the length of our curve, or the curve length. And we have the point of intersection between the two tangent lines. This is what we call the PI. And the angle between these two tangents is what we call the I, in which that is equal to the central angle here. Okay, so this is I as well. And then we have other element here, that is the distance between PI to the midspan or the mid-length of our curve. Again, that one is E, or the external distance. And from the mid-length of our curve to the mid-length of our chord, that's what we call the middle ordinate, or that's the M. Okay, so we will derive all the formula to compute for this element of our simple curve here. Okay? Now take note, in the properties of a circle, this angle here is always 90 degree, or the angle between the radius and the tangent line. So the angle here as well on the side of PT, on the side of our forward tangent, is 90 degree as well. Okay? And this angle here, again, this is 1/2 of our central angle, or that is I over 2. Okay, now take note of that. So the first thing that we compute here is the formula, or the length of the tangent. Okay, that is the length of our forward tangent and the back tangent. So how are we going to compute our T here? Now take note, this is a right triangle. So if we connect from PI to the center of our circle, this is a right triangle, correct? In which the angle here is 90 degrees, and this one is our tangent, and this one is the radius, and this length here from PI to the center of our circle is equal to E plus, now take note, this is the length of our radius from this point towards the center, that is the radius. Okay, so therefore this one is E plus R. That is the length from PI to the center of our circle. Okay, now how are we going to compute for T, or the tangent? So, however, we need to have an angle here. The angle at this point here is 1/2 of our central angle. So this angle here is I over 2. Okay, that's the 1/2 of the angle of intersection. So therefore, this is I over 2. So we can now compute tangent here by just using one of trigonometric identity. So we can use tangent. So we have tangent theta is equal to opposite over adjacent. Okay, that is from the most common mnemonics, or the most important mnemonics, which is SOHCAHTOA. Okay, when we're in TANHI, there is tangent is equal to opposite over adjacent. Now in this case, tangent of our angle here, which is I over 2, is equal to the opposite of I over 2, which is T, over the adjacent side of our I over 2, which is R, correct? So therefore we have T is equal to R tangent of I over 2. Okay, so this is the formula for the tangent length, or the length of our forward and backward tangent. So we have done with our first formula, which is the tangent distance. Then we compute for the element M, or the middle ordinate. That's the M. So how are we going to compute for the M? So we can extract this triangle, okay, this triangle here, in which this angle is 90 degree. Okay, that is always perpendicular to the chord of our simple curve. Okay, so if we extract that triangle, then we would have this one, in which the angle here is still the same, it's still I over 2, and we have r here, that's the radius. Then we have the length from PC to this point is 1/2 of our chord, that is C over 2. Okay, since again this one is C over 2 and this one is C over 2 as well. And then we have here 90 degree. Now, what would be the length of this side here? Okay, again, this is the center of our circle. Now, the length of that is r minus m, or the middle ordinate. Since again, the distance from the midpoint of our curve to the center of our simple curve is the radius, correct? And then we subtract the value of our m, hence we have this length here. Okay? And that we have r minus m. So we can use trigonometry identity, which is cosine. We have cosine I over 2, which we know that cosine theta is equal to adjacent over the hypotenuse from the mnemonic SOHCAHTOA, in which cosine I over 2 is equal to the adjacent, which is r minus m, over the hypotenuse. The hypotenuse of this right triangle is r, or that's the radius. So by further simplifying, we have r cosine I over 2 is equal to r minus m. So basically, we just cross multiply. Then we have m here is equal to r minus r cosine I over 2. So we transfer m on the left side, while r cosine I over 2 to the right side. So we have m here. Now we can factor out r. So we have 1 minus cosine I over 2. So this is now the formula for the middle ordinate. Now, after middle ordinate, then we can now compute for E, or we can now derive the formula for the element E. This one is what we call the external distance. That is the distance from PI to the midpoint of our curve. Okay? So, how are we going to compute this one? So, we use this triangle again. So, this triangle, in which that is a right triangle, in which again this one here is 90 degrees, and then we have T, that is the tangent line. Okay, now this one is the r, or the radius, and the angle here is I over 2, or the half of our central angle. How about this side here? From PI to the center of our circle, now again we have r plus E, or the radius plus the external distance. Okay, since again from this point to this point is the radius of our circle. So using the formula, or the trigonometric identity, which is cosine, okay, cosine of I over 2, and we have the adjacent r over the hypotenuse r plus E, correct? And then we have to cross multiply, then we have cosine I over 2 times r plus E is equal to r, correct? So we can distribute cosine I over 2 inside the parenthesis. Then we have here r cosine I over 2 plus E cosine I over 2 is equal to r. Okay, so we can group common terms. Okay, so we have E cosine I over 2. So we can transfer r cosine I over 2 to the right. Then we have here r minus r cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we divide both sides by cosine I over 2. Okay, so we then here as well. So we can cancel cosine I over 2 here, so the remaining would be E. This equals to, okay, so we have R over cosine I over 2. However, we can cancel cosine I over 2 here and this one, so the remaining would be R. So we have minus R. So we have E is equal to, now take note we can factor out R. So the remaining would be 1 over cosine I over 2 minus 1. Okay? Now we know that 1 over cosine is just the inverse of secant theta. Correct? So we can say then that R times secant I over 2 minus 1. Okay? Hence, we have now the formula for the element E, or the external distance. Now, our next goal is to compute for the formula for our C, or that is the chord distance, or that is the distance from PC to PT, or this line here. Now, to compute for that distance, we can extract this triangle, in which this is still a right triangle, wherein this side here is R, this one is PC, and this one is O. Now, the length here is C over 2, that's the 1/2 of our chord distance. And then the length from this point to this point is R minus M. And the angle here is I over 2. Okay, so our goal here is to compute for C. So we can use sine. Okay, so we know that sine is the opposite over the hypotenuse. So sine I over 2 is equal to its opposite of angle I over 2, which is C over 2, correct? Over the hypotenuse, which is R. So we have here C over 2. Now we cross multiply. We have R sine I over 2. Hence, we have the chord length, the total chord length, which is 2R sine I over 2. Again, that is the length formula from PC to PT. So again, this is our element C, or the element chord length. Now, our next goal here is to compute the length of this curve, or our LC. Now, from our geometry, we know that the length of the arc of a circle is basically equal to S is equal to R theta. That is from our geometry, in which if this is a sector of a circle, in which this length here is the S, and this is the R, the radius of our circle, and this is the central angle theta. Okay, so that's how you compute for the value of S, or the length of this arc. Okay, so basically we will be applying this formula to compute for our LC, in which in this case our S is LC, or that's the curve length, and then the radius R. Now theta, that is the central angle, which we know that's I. Okay, that's the angle here. So, however, take note I here is in degree. So we need to convert this one into radian. So how are we going to convert that one? Now we know that in 180 degrees, that is equivalent to pi radian, correct? So therefore, we need to multiply this I here by pi over 180. So we have LC is equal to R, I, times, you convert since this one is in degree, so we multiply it by pi radian over 180 degrees, so that we can cancel out degree, correct? The remaining angle would be in terms of radian. So therefore, the length of our curve is equal to Ri pi over 180 degrees. Okay? So this is now the formula for the length of our curve. So we have derived all this formula here. So if you forget this formula, now during the examination or during your board examinations, then you can derive. Okay? So that is in case of emergency. Now we also have other element here, which is we have D. Now D here is what we call the degree of curvature. Okay, this measures the curve sharpness. Now what's the purpose of D? Now D here is our deflection angle. Now we have two different methods in computing for the degree of curvature or the degree of sharpness. We have degree of arc basis, this one, and we also have the chord basis. So we will be deriving this formula. Now the purpose of the degree of curvature is to locate the points along the curve. How does it help in finding the points on our curve? Now, D here is our angle of deflection. Now, in layouting simple curve, we usually use PC here as the initial position of our instrument. Okay, so this is where we put our instrument. Then, in locating our point, so the first thing we do is we sight PI. Okay, so we positioned our telescope parallel to our tangent line. So that means the line of a sight should be parallel to this tangent here, correct? Now, once we sight PI and once we find PI on the telescope, we set our angle here or horizontal angle here as 0, then we deflect. Then that angle there, that deflection angle here, D, that is where the location of our point. Okay? So meaning, this D here, that is the angle of deflection so that we can locate our points on our curve. Now, points here, this is our station. Now, in DPWH, the distance between station to station is 20 meters. Okay, take note of that. That is the distance between stationings in our simple curve. Okay, so that's the purpose of D again, to locate all the points on the curve. Now, D here is also the measure for the sharpness of our curve. Hence, this is called as the degree of curvature. Okay, since, again, the larger the D, okay, or the greater the degree of curvature, that would gives us the lesser the radius. Pag masyadong maliit ang ating radius, the sharper the curve would be. Okay, so the lesser the radius, the sharper our curve. When we design curve, we make sure that our curve should be smooth as possible. Okay, since again, pag masyadong sharp ang ating curve, that would cause accident and that would give us higher centrifugal force. So if we have a car running on a fast velocity, okay, so therefore that would give us a greater centrifugal force. Okay, so therefore we make sure that our D here, or the degree of curvature, should be small as possible. Okay, should be lesser as possible, because this would give us greater radius. Okay, so therefore the smoother the curve, which should be the desired design for a simple curve. Okay, so that's the purpose of D. Now again, we have two different approach in computing for the radius given the degree of curvature. We have the chord basis and we have the arc basis. So what would be the basis of these two bases? Okay, now for chord basis, we let 20-meter distance here as a chord. When we say chord, that is a line connecting station to station, like this one. Okay, so this is 20 meter. Now we have other chord connecting other station. Again, the desired or the length adopted by the DPWH is 20-meter station distance. Again, the station distance adopted by government agencies such as DPWH is 20 meters. Okay, so again, we know that the angle here is D. So therefore, if we have D there, we have degree of, if we have value of degree of curvature between PC to, let's say this is 0 plus 0.20. So therefore, the angle between the two radii, okay, subtended by this radius here is also d, correct? So we can say then that for chord bases, we let 20-meter distance here as a chord, okay? So we can extract this triangle in which this distance here is 20 meters, correct? And we have the radius, and this one is the radius, and the angle or the central angle here is the d, or that is the degree of curvature. Okay, so our goal here is to determine the r. Now we can divide this one into two right triangles, in which this is a right triangle, and the angle here is 1/2 of our d, which means this one is d over 2, correct? So therefore, our length here is 10 meters and 10 meter here as well. So we can say then that sine of d over 2 is equal to the opposite of d over 2, which is 10, over r, correct? So therefore, r is equal to 10 over sine d over 2. So this is now the formula for radius when we have degree of curvature using chord bases. Now for arc bases, instead of having 20 meter here as a chord, we set 20 meter here as the arc instead. Okay? So instead of a chord, so we let this arc length here, again this arc length here as 20 meters. Okay? That's for arc bases. So that is 20 meters. So we can isolate this sector of a circle in which this arc here is 20 meters, that is from station to station length, and the central angle here is d, or that is the degree of curvature. So we use the formula S is equal to r theta. That is S again, that is the length of the arc, in which we have there 20 is equal to now our radius r. Again, this is r. So r, then theta here, that's d, correct? That's the central angle. Now again, d here is in degrees, so we convert this into radian by multiplying pi over 180 degrees, since we can cancel out degree and the remaining unit here is in terms of radian. So we have r here is equal to, okay, so we can cross multiply 20 times 180 over d pi, correct? So we cross multiply, so we have r here, which is equal to, now we can actually compute the value of this one, in which we have 1145.916 over d. So this is the value of our radius given the degree of curvature using arc bases. The difference between arc bases and chord bases is that in arc bases, we let 20 meters there as the arc length, whereas in the chord bases, we let 20 meter distance there as distance between station to station as a chord, as the line connecting station to station. Okay? And that ends the derivation of important elements in our simple curve. And now in my next video, we will try to apply this formula in solving problems. And I will be giving you the link of the part 2 of this discussion on the description below. Alright guys, thank you for listening, but please don't forget to like this video, share, and subscribe to my channel. Thank you guys, and have a great day.